Let's start chapter 5.2, which is called Definite Integrals. Let's step back and do an overview of where we've come from and where we're going. I've said Calc 1 is all about how fast things are changing and how much they've changed so far. So what's a good calculus word for how fast things are changing? Probably derivative, right? And then what's a good calc word for how much they've changed so far? Well, we haven't really talked about that, but we're getting into that. That's integrals. And in calc we have two big ideas, and one of them we've seen already and the other one we're launching into. If you zoom in enough, most of the common functions we use look what? You'd say linear. That's the whole tangent line idea, right? And then if you have the new one is if you have a hard problem, let's break it into easier pieces or steps and then put it all together. Have we done that at all this semester? We actually have with our calculus prediction equation, where we've said, here's our rate of change function, let's say what the original function is doing. We've broken that into little tiny steps all the way along. So our calculus prediction equation. And we've talked about differential equations, and there was something called Euler's method. And those are basically the same. Just two different ways of looking at it. So we've done a little bit of that so far, and then we're going to see that approach more and more in chapter 5. So here's an overview of what's going on in chapter 5. We've already talked about indefinite integrals, and they give you a function which seems like it's not all that exciting, but it's actually an infinite amount of information. You give it an x value, it gives you a y value. So that's a whole description of everything that's going on. In chapter 5.2, we're going to do something called definite integrals, where we're going to write the integral sign with some kind of number at the bottom and some kind of number at the top, or variable. And that just gives you a single value, which feels a little more definite. It feels like, oh, I got this answer, I can go check whether this answer is right, but it's actually a lot less information than a function. So we're going to define them kind of intuitively in chapter 5.2, and then in 5.3 we're going to define them more rigorously. And then in chapter 5.4 we're going to see how these two ideas relate to each other. And that'll be the fundamental theorem of calculus. And they don't call it the marginally important theorem of calculus. I heard someone once say it's pretty big and important, and we'll get there in a few days. So let's start a little example problem that we'll be using to understand this new idea of definite integrals. The distance you've driven, let's say you're only driving forward, or the net distance you've driven, is how much your what has changed. If you said, I drove 5 miles, or rode my bike 5 miles, or whatever, that's how much your position along a number line has changed, right? So it's how much your position has changed. So let's take a sample driving here. You could pretend these are kilometers if you want to be a rational person. If I drive 50 miles an hour for 1/2 hour, and then 40 miles an hour for another 1/2 hour, and then 60 miles an hour for 3 hours, how much total distance have I driven? You can probably do that, but let's maybe even in your head, but let's try to do it in an organized way. What's the distance driven for that first segment? You'd say it's 50 miles per hour times 1/2 hour, and the units cancel nicely, and you get 25 miles. Let's zoom in a bit. For this one, it would be 40 miles an hour times 1/2. You get 20 miles, and here 60 miles an hour times 3 hours gives you 180 miles. But let's say also, how far have you gone so far? Well, by the end of this time block, you've gone 25 miles, right? Actually, I want to draw that over here. How far have you gone total by the end of this time block? You went the 25 plus the 20 that you just drove or rode. So you'd say it's this 25 plus this 20 gives you 45. And then how far have you gone total by the end of this time block? You'd say it's this 45 plus this 180, which would be 225, right? So altogether, we went 225 miles, and we kind of just did that big idea of if you have a complicated problem, break it into small blocks and then put them all together. Here, we had our interesting driving behavior. Maybe we were in a traffic jam or something for a while. And to get the total amount, we broke it into small bits and then added them all together. So that's a fairly straightforward calculation, hopefully. What's left to do? Maybe graph it. So take a sec, sketch out a graph, and then pause the video while you're doing that. All right, welcome back. So what does our graph look like? Well, usually if there's time going on in a problem, we put that on the x-axis. So we'll put time here, 0, 1/2, 1, and then out here is 3. And what we were given was speeds, so let's put that here. Let's say here's 60, here's 50, and here's 40. And this axis is our velocity at time t in miles per hour. What's another name for velocity in calculus? It's the derivative of position, right? And what was my speed for that first half hour? It was 50. So I could say it was 50 there, and then it was 40 for a half hour, and then it was 60 for 3 hours actually. So this should be 4. All right, so that's what my velocity did. And how can we interpret what was going on here, these calculations, in terms of what's going on with this graph? Like, how would I interpret 50 miles an hour times 1/2 hour is 25 miles? Well, I've got my 1/2 hour here and my 50. And if I just saw this without the units, I would say, oh, 50, a height of 50 and a width of 1/2 is the area of a box whose height is 50 and whose width is 1/2. So I could say this area of a rectangle is 50 times 1/2. Is that really an area? Well, its answer is 25 miles, and miles are not an area. So we're using area of a box as kind of an abstract model for the multiplication that's going on. We're not literally saying this is area. We're just saying you can kind of think of it the same way you think of areas for real boxes on paper. So instead of saying area, we're going to put area in quotes. So it's kind of not really area, but it's our model. It's an area model for multiplication. So the area of this rectangle is 50 miles per hour times 1/2 hour, or 25 miles. And then you could do the same thing for this one, for this rectangle, and for this rectangle with the appropriate numbers. So other things we call this is area under a curve. Now this isn't very curvy, but when we deal with nice smooth functions it is. So it's also called area under a curve, or under the curve. Or you could say it's the area under the v of t function, but stopping at v equals 0 or at the x-axis. We're not going all the way down to negative infinity. Now I'm putting area in quotes here because it's not really area. In this case, it's miles. But if you're writing stuff out in the homework, you don't have to put area in quotes. I'm not going to be picky about that. All right, so what's our total distance traveled by time 4? What's a name for that? Well, if I started at position 0 at time 0, where am I at time 4? S of 4 would be the name for that. We know above we calculated it at 225. But what's a way of interpreting it from this graph? It's this box area, which was 25 miles, and this box area, which was 20, and this box area, which was 180. So it's the sum of the 3 box areas. When I say box here, I don't mean a cardboard box that's 3-dimensional. I mean a rectangle in 2 dimensions. So the sum of those 3 box areas was 225, and that's how far we had gone by time 4. But we can also see the sum of those 3 box areas as the area under the v of t function or curve. And because v of t is also called s prime of t, we could just say it's the area under the s prime of t function. So next we're going to take all these sort of complicated calculations we did. I mean, it's not really that complicated. And look at kind of an easier way to get a kind of rough guess or an idea of whether our more complicated answer is reasonable or not.